Yes, good afternoon to all the participants. Hope you can hear me.
Yes, sir. Yes, sir.
Thank you, sir. All right, so uh, we'll start from the point where we left off yesterday. Okay, right. So there are two topics given for me to be discussed for yesterday and today, right? Uh, just a minute. Yeah. So two topics were asked me to discuss to ensure these two topics were conveyed to the participants. So one is, as you can see on my screen, one is numerical integration. Okay, and under numerical integration, we're supposed to discuss linear second order differential equations, ordinary differential equations with a constant coefficients. That is one of the type. The other type is again linear second order differential equations, ordinary differential equation with variable coefficients. Okay, right? And among these, some boundary value problems, because all our quantum computing quantum systems are actually boundary value based dynamical systems. So we need to discuss a little bit on that also. Okay. So the way I designed today's session is divided into three sections. Okay. So I'll have three sections. One is numerical integration. We will discuss about numerical integration. Okay. In one of the section. In another section, we'll talk about ordinary differential equations, which will be multiple types. They are called linear, non-linear, and also called homogeneous, and also non-homogeneous. Okay, right? So if you want to divide ordinary differential equations into first order and also higher order. Higher order in the sense second and third order onwards. Okay, so differential equations are divided. Okay, there may be a homogeneous linear differential equations. There may be homogeneous non-linear differential equations. That is also possible. Okay, homogeneous and non-homogeneous. We will come to that. What are those? And this one applications. So boundary value problems. So this is how I divided the today's session. Okay. So before going into the numerical integration, what I would feel, okay, better to discuss some types of differential equations and we'll get to know the details and then we'll go ahead. Okay. So ordinary differential equations. Okay. Or if you want, I can just say only differential equations as of now. Differential equations are the ones going to have, they're going to have derivatives. We know that. Okay. Derivatives we are going to have, and also we are going to have functions depending on functions depend on independent variables. Okay, right? So this is what differential equations, by the way. So let's take a simple example and try to understand them. So let us second order derivative of some function f of x, and it also has first order derivative, and it also function itself it has, and which is equal to some sine of x. So this is an example differential equation. Using this example, we'll try to understand details. Okay, here you see the derivatives are directly proportional, okay, related to second and first order. Okay, so derivative of function of second order, derivative of function first order related to f of x directly. Okay, right? So you can say these are like linear differential equations, right? Okay, so let me go a little bit. Let me simplify this. Okay, uh, uh, let me take some function dy of x by dx is equal to y of x. The simplest scenario, simplest case. Okay, so as you can see here, derivative is directly proportional to the function itself. Okay, derivative of y of x is directly proportional, okay, proportional to y of x. Okay, if such feature is there, you know what happens? If such feature is there, these functions are going to have exponential solutions. You know why? We know that. We just take this, rearrange dy of x divided by y of x is equal to dx. Just a rearrangement. Now you integrate. Okay. So let's say I don't know about the limits. I can leave it without limits. Integrate log of y of x is equal to x plus some constant. Okay. Right. So let me call this some constant c prime. You know why c prime? I'll tell you. You send the log, natural log to the other side. Y of x is equal to exponential x into exponential c prime. I'll call exponential c prime as some constant c exponential x. That's why I introduced c prime instead of c earlier. Now if you see, this is a linear differential equation. So linear D is possess, okay, exponential solutions. Okay, you can also say sinusoidal solutions if you want, right? So it is that simple and that easy to find. Look at this equation, immediately you can just figure it out. What are the solutions? Only thing is some constant is there. I need to find out what is that constant. Okay, in real world example, real world example, real world example. Okay, real world example, if I have to give, you know, right, a falling object. Okay, real world example is a falling object. Falling object. You know, what is the falling object? What is the force acted upon the falling object? It is mass of the object into gravity, acceleration due to gravity. Okay, right? So the gravity is acting downwards. So you can have minus sign if you want. And what is the motion of the object? Object motion is d square divided by dy t square. Okay, which is equal to mass into acceleration is equal to minus mg. M cancels. So what I left with dy by dt square is equal to minus g. Okay, fine. So this is a differential equation. Here I see g is a constant. Okay, it's not a function. So the derivative, second order derivative is becoming a constant value. Okay, now if I want to have the scenario what I was expecting in the previous case, let's take some air resistance is exerted on the falling object. Okay, now consider air resistance. So how do I introduce air resistance is, I will introduce some kind of a frictional force Fr, which is usually depends on the velocity of the object, and this always opposes the velocity of the object, negative fashion. So if I had to write down what is the explicit value of frictional force, okay, which is equal to some constant k into dy by dt. This is a frictional force for you. Now, if I add this into the above equation, okay, so above equation was m into d square y by dt square is equal to minus mj. Okay, the resistive force again, it is going to be, so see, something is moving down, so the resistive force is going to move up. Okay, so going to oppose, so I'll have my plus sign opposite the gravitational force, which is k into dy by dt. Okay, so you just rearrange this entire equation into one side. What I'll have, okay, plus k by m. If you divide the entire equation by 1 by m and then rearrange dy by dt minus g is equal to 0. Now you see, I have at least first order derivative inside the equation and second order derivative inside the equation. Probably I may not have a y function in it, but at least I have first order derivative in the equation. Okay, fine. So this is a real world scenario. Now let's see exactly what I was expecting. Okay, so let's say a differential equation, another example, derivative of a function is directly equal to the independent variable. So what I mean, the derivative with respect to x is written as y dash. If I have to write a derivative with respect to time, I'll put a y dot. Dash stands for some independent variable is equal to x. Okay, so dy by dx is termed as y dash. Okay, so now if you see this expression, you just try to solve it. This would be dy x into dx integrate. Let's say I don't know what is a constant. Limits. This is a y is equal to x square plus some c. Okay, x square by 2. You should not forget the constant. Okay, so the solution is some quadratic function. Okay, if you see now, you try to plot y of x versus x, what you get is, so y is going through the center, okay, going through the, it's a parabolic function, not a v, I just draw it like this. Okay, so where here x is equal to 0, sorry, c is equal to 0 for this curve. And if I have some non-zero c, I'll have something like this, c not equal to 0. Okay, I may have one more, c not equal to 0. Okay, exactly what is the c value here? If this is the value is equal to -1, c value is equal to -1. If this is equal to +1, c value would be equal to 1. Okay, so this is a, if the derivative is equal to the independent function, I have a solution for curve 2. Okay, right? Okay, now let's go a little bit further. Okay, so what is little bit further I want to know? I want to have a solution like a differential equation. Okay, like this time I'll say y double dash means second order derivative of y minus y dash plus 6y. Let's choose dependent variable inside the differential equation. If I have a differential equation like that, if you can see now, here y double dash and y dash are proportional to y. So it is a linear differential equation, linear TE. So what do you know? Whenever I have a linear differential equation, straight away you can say it is going to possess solutions of exponential type. Okay. So by cross checking, you can find, say, exponential 2x is a one solution, exponential 3x would be another solution. And you can ask me, how did you get these values? You can find by trial and error method. Okay. Or you can find introducing y1x is equal to some exponential mx. Okay, let me substitute in the above. What it will have is d1 dy1 by dx is equal to m into exponential mx, which also implies second order derivative of d1 is equal to m square exponential mx. Okay, which means I substitute in the above, I'll get m square exponential mx minus 5 into m exponential mx plus 6 into exponential mx is equal to 0. I take exponential mx common and I can send it to other side, it becomes 0. So what I am left with, m square minus 5m plus 6 is equal to 0. It's a quadratic equation in m. So I can say m square minus 3m minus 2m plus 6 is equal to 0. So you take a m common, m minus 3, 2 common you take, m minus 3 here is equal to 0. So I'll have two solutions for m. What are those solutions? M is equal to 2 and 3. So which implies there is a solution which is exponential 2x. Another solution is exponential 3x. Okay. So for a linear function, this is how I am going to find the solution. Interestingly, for linear functions, okay, and these functions are also called homogeneous functions because I don't see anything on the other side of the equal symbol. So these are called homogeneous differential equations. Okay. So in that case, the beauty of the differential equation is I can get some general form. We can always obtain some general solution from known solutions. I have two solutions. From there I can derive one other solution, which would be y of x is equal to c1 exponential 2x c2 exponential 3x, where c1 and c2 are some constants. Okay, some constants, right? So this is how linear homogeneous differential equations are going to possess some solutions like this. Okay, right? So if I know if boundary values are given, boundary conditions are given, then we can easily find the constants what we saw here, C1 and C2. You can easily find those constants. It's straightforward, that easy. Okay, so example, let's say for your sake, let's take an example. Example is D with boundary conditions given. Okay, I'll take one simple example from the notes. Y dash is equal to 2y. That's simple. Okay, and the condition given is y of 0 is 1. Boundary condition is given. So usually they even give a boundary condition for derivatives when they give higher order derivative differential equations. Okay. Now, as you can see, it's a linear differential equation. Straight away, you can plug in the differential equation will have solutions of some constant time exponential some mx, and from there you can find out the solution of this differential equation is c into exponential 2x. Okay, I don't know what is c. What I'll do, I'll substitute the condition y of 0 is equal to exponential 0, which is equal to 1, which implies c is equal to 1. That's simple. Therefore, y of x is exponential 2x. It's even the general solution for this differential equation. Okay. Sometimes, let's say some people give, for example, one-dimensional box where x is equal to L. In that case, the y function is, let's say, some 20. In that case, what happens? Y of x is equal to L is equal to c into exponential 2L is equal to 20. Okay, right? So, which implies what is c? C is 20 by exponential 2L. Now, what would be my solution in this case? The solution would be y of x is equal to 20 by exponential 2L multiplied by exponential 2x. Therefore, what is the solution? Solution is 20 into exponential 2x minus L. Okay. See, having a boundary condition, okay, we can find much more detailed solutions. Okay, boundary values are highly useful in finding exact solutions. Okay, right? So let's go few more simple scenarios. Okay. Now, for example, I have a differential equation, little bit tricky. Okay, some tricky differential equations. What is the trickiness is? Let's say I have a differential equation y dot is or y dash is equal to 2 into xy. I see now here in this case, the derivative is not directly proportional to y, even it is directly, but dependent variable x is also there. What I will do in this case, okay, dy by dx is equal to 2xy. Let me do separable method. Dy by y is equal to 2x into dx. This is called variable separable method. Variable separable method means I am putting different variables on one side. Now let me integrate. When I integrate, natural log of y is equal to 2x square by 2 plus some constant. 2 cancels. I'm in a class. Okay, right? So 2 get cancels. What I left with x square plus some c. Instead of saying c, I'll say c prime. Okay, why c prime? Okay, why c prime is when I send a log to the other side, y is equal to exponential x square into exponential c prime. I will call exponential c prime as some c. Okay. Now you see y is okay. Y is c into x square. Right. Now similarly, another example is y dash is equal to x square plus y square. This is a little bit more tricky. Okay. So in this case, how to solve? You can follow the same method. Okay. But this time what you do, you introduce some polar coordinate system, convert x and y in terms of polar coordinate and try to do it. Hint, polar coordinate system. Okay, so in that way it is much easier, it becomes. Okay, so x square plus y square, you know, x square plus y square is equal to r square. Okay, in the case of polar coordinate system. So it's r square. You convert x and y in terms of x is r cos theta, y is r sin theta. Okay, and dy by dx is derivative. Okay, so derivative with respect to x. So instead of taking a derivative with respect to x, you take a derivative of y with respect to theta, take x with respect to theta. Okay, so which would be, let's say r is constant. Okay, so in that case, r cos theta d theta divided by r minus r sin theta d theta. So r cancels, okay, right? D theta b theta cancels. Okay, I'll get dy by dx is equal to some cos theta by sin theta. Okay, by the way, what is dx? Dx is r into, okay, r into variation in cos theta is sin theta minus d theta. Dy is minus plus r cos theta d theta. Okay, so you can just try to do in this way and reduce this into integrate derivative. Okay, reduce into polar coordinate system. Then you can find the solutions easily. Okay, keep that aside. Now, first order differential equations with the variable coefficients we want to know. Okay, so far we have seen linear differential equations with the constant coefficients. Now let's say I have a linear differential equations with linear dE with the variable coefficients. Okay, what are those? Let's say y dash plus ax into y is equal to bx. Okay, now you see constant a, earlier I had a multiplication to the function is a constant, now it's a variable, and on the other side also I have some constant which is also something which is also function of some x. Okay, so these are like variable constants or variable functions. So I would say, even though it appeared to be linear, okay, and you can say it's on the other side of 0, so on the equal symbol, if there is something is there, it's a inhomogeneous function. Okay, right? So these are like variable functions. Now, how to find the solutions for them is little bit different from whatever we have seen so far. Okay, let's take an example, finding solutions. Okay, right, take an example. It is best in that way instead of generalizing. Okay, so what I will do, y dash plus ax into y is equal to bx is there na? Okay, I'll say it has a solutions like exponential of a of x into dx as a solution. Okay, is the solution, let's say, is a solution of above equation. How did I get this? As we see, if there is a constant coefficient, I simply has exponential of some mx is a solution. But here I have a variable coefficient, so I will, instead of having m, I will take a variable as a thing, and I'll also add the integration. Okay, what I will do now here is, when I compare whatever equations I may be having, okay, from there I can find what will be the ax. Okay, so one example I will be taking is Okay, y with ax is equal to some 2x and bx is equal to some x. Okay, what I mean by that is the equation is 2xy is equal to x. This is my differential equation. From here, what is my corresponding solution? Exponential 2x dx, which is, okay, exponential, okay, 2 you can get it out, x into dx, which is exponential to x square by 2 plus some constant. You just for time being don't worry about the limits. So okay, what is the result? Exponential x square. Okay, right? So now let's see whether y of x is going to, if this is a solution, is it going to satisfy our equation or not? Let's check. Okay, let's check for y of x for the above equation. Okay, let's check that. Okay, right? Yeah, right. So yeah, so somebody was pointing out in earlier case, yeah, minus sign or something. Yeah, I'm sorry. Just roughly was going through. So yeah, you please correct it if there is some mistake there. Okay, right. So yeah, there are other things. So many things are there. So that's why I was hurrying. Now here in this case, I'm just trying whether given exponential x square could satisfy our equation or not. Right now, if y of x is exponential x square, which means what is the y dash? Y dash is exponential x square into 2x. Okay, right? So that is very good. Hmm? And yeah, yeah. So now what I will do is to integrate the entire equation, this equation much easily. What I will do, I'll just multiply this entire equation. Okay, let's convert the above equation into easily integrable form. Easily integrable form. Okay, right? Okay. Now, how do I do? I just multiply the entire equation by exponential x square. Y dash plus 2xy is equal to x. Okay. When I do it, what happens you see? Interestingly, ex square y dash plus exponential x square 2xy equal to x dx into exponential x square. Now, if you look at the left hand side carefully, what it is? It is actually a derivative of exponential x square into y. Okay, let's try to do this. This would be dy by dx exponential x square plus y into 2xy into exponential x square. Sorry, y is already given. So this is what I have. So what I will do, the left hand side I replace it by, what I'll do, left hand side I'll replace it by, 1 minute. Okay, so the left hand side I replace it by the derivative of exponential x square into y is equal to x into exponential x square. Okay, now on the left hand side I have e exponential x square, on the right hand side also exponential x square, but what I will do, I will send the dx onto the other side. Derivative of exponential x square into y is equal to x into exponential x square into dx. Now you see on the right side at least I have only x terms. On the left side I have a derivative of some x and y function. Okay, so if I integrate left hand side left, I'll get derivative cancels the integration, so ex square into y is equal to, so now I have algebraic function and exponential function. What I will do, I will just introduce x square is equal to some t. Okay, for this case x square is equal to t means 2x into dx is equal to dt. So x into dx is equal to dt by 2. Okay, which if I introduce that, this integration would be, okay, the exponential t, okay, dt by 2, which is half into exponential t. That's all. Okay, with some constant if you want. So the value on the other side is, you replace back what is t, t is x square, 1 by 2 exponential x square plus some constant. Okay, which implies y is 1 by 2 plus c into exponential minus x square. You see, even there is a complicated scenario, just like the product of dependent independent variable are there, what we can do, we can multiply the entire equation by some factor exponential of some mx, some exponential of some function, and then convert the given differential equations to easily integrable form. Okay, right, easily integrable form, this form. The moment you do that, okay, so you can find the solutions easily. Okay, this is a one more technique, right? So there are other ways. For example, if I have a differential equation which is like, okay, y dash is equal to p and y double dash is equal to p dash. Okay, if this kind of a differential equations are given, this is second order differential equation, how do I solve in this case? Example. Okay, so example is x y double dot or double dash minus y dash is equal to 3x square. Okay, and y dash is equal to some p. Okay, where p, I don't know, let's say some functional form which has a derivative. So p is dy by dx. Okay, so if I had to find the solution, I can just reduce this to a p dash 1 by x, okay, into p is equal to 3x. Right? Now if you see, it's a derivative equation for p with respect to the independent variable x. So you can easily solve this now. Okay? So a second order differential equation could be reduced to first order differential equation. Okay, from here you can see second order dA could be reduced to first order dA by introducing a variable, example, velocity variable. Okay, velocity. In this case, p is like a velocity. If x is time, y is some distance. Okay, right? So if you want for the workout, I can give one more example from the notes. Y double dot or double dash. Okay, y double dash plus k square into y is equal to, where some k is some constant, is equal to 0. So this is second order dE. What I'll do? I'll introduce a variable as a velocity component like y dash is equal to p, which implies y double dash is p, okay, derivative of P, okay, so derivative of P dP by dy dy by whatever independent variable which we will be choosing, which is, let's say, dx. Okay, so from here already we introduced y dash is equal to P, so this would be P into dP by dy. Okay, so you have this conversion which is P into dP by dV plus k square. Okay, k square y is equal to 0. I can easily find what will be the solution of this differential equation by whatever method we seen so far. We can convert this into easily integrable form and then find the solution. Okay, right. Now, second order linear differential equation I want to solve with the constant coefficients. Okay, second order linear differential equation with the constant coefficient, that is one of our target. Okay, right, second order linear differential equation with the constant coefficients. It can be inhomogeneous, okay, so I'll talk about inhomogeneous. So far we have seen homogeneous ones. Inhomogeneous ones are some a constant coefficient dy d square y by dx square plus b into dy by dx plus c into y is equal to some d. So it's nicely written in terms of ABCD, where ABCD are some constants. Okay, so real world example, again you can say a falling object or some object moving due to some force. So where F is equal to ma. Okay, so in fact that is the most simplest example for this kind of differential equations. Okay, right. So what I'll do first, reduce this to homogeneous case. First we'll deal with homogeneous and then we'll come back to non-homogeneous. So I introduce gd equal to 0. In that case, what happens? A into y double dot, sorry, y double dash, b y dash plus c into y is equal to 0. So this we know already. This is going to possess a solution of exponential solutions. Some y of x is equal to some rx. Let's say I don't know what is r. What you do? You can substitute this back into this equation and find out r. Okay. So let me do that. Y double dash would be giving me r square erx. Y dash giving me r erx. Okay. So if you introduce this back into the equation, I'll have r square a exponential rx, r into b exponential rx, c into exponential rx is equal to 0, which implies ar square plus br plus c is equal to 0. Okay, this is a quadratic equation in terms of r with some constants. Okay, now if you see here, either this is equal to 0 or exponential rx is equal to 0. Only two solutions are possible. Exponential rx cannot be 0 because exponential rx cannot be 0. To have this is equal to 0, x has to tend to minus infinity. Okay, and r is greater than 0. Fine. So you forget about that. Let's worry about what is the quadratic equation solution. Okay, so which would be minus b plus or minus square root of b square minus 4ac divided by 2a. So somebody gives you a quadratic equation, sorry, differential equation with a constant coefficients. What you do? Straight away find the r values, and from there you can find the general solution of homogeneous part, which is exponential ERX. Let's say there are two solutions with R value R plus and minus, R plus B into R minus X. Okay, right? For your sake, I can give one example for practice. You can do it. Example for practice. Okay, right? From the notes, I can give you one differential equation would be, okay, let me give you from the notes, y double dash minus 5y prime plus 4y is equal to 0. This is one equation. Another equation is 2y double dash plus 6y dash plus 2y is equal to 0. Okay, so you can try finding the solutions of these things, whatever practice we did so far. Okay, right. Yeah, sometimes the roots may not be that easy. The roots may be a complex roots. Okay, whenever the solutions for R are complex. Okay, so in the above two cases, solutions may not be complex. Let's say you take an equation y double dash minus 2y dash plus 5y is equal to 0. In this case, if you take, the solutions are actually complex solutions. Okay, so why? Because the R values comes out to be, from the notes I'll write down, is equal to 1 plus or minus 2i or I2. Okay, so the complex solutions are there. What you can do, you can express the solution in terms of this complex constants. Okay, right. Now after that, now going back to non-homogeneous part. Okay, now tackle non-homogeneous or inhomogeneous. What I mean are inhomogeneous. Okay, now tackle it. How do you tackle? Okay, so a y double dash plus by dash plus cy is equal to some f of x, some constant is there on the other side of equal symbol, that is the inhomogeneous part. Now I want to find a solution for this case. So now let's start with some initial solution, which is something like y naught x. Okay, right? So it is a y naught x. Now if I add some, multiply some constant to that, I'll get some y naught of x. Okay, now let's say y naught x is a solution of homogeneous part. Now I multiply with the a. Let's say I assume that this is the solution for the entire equation. Okay, I assumed. Let's see that. Now if we substitute back into the above equation, okay, LHS, what happens? I'll have a, I'll get okay, so y, yeah, y, okay, so what I'll have, a into y naught double dash plus b into a into y single dash plus c into a y naught LHS. So which is going to be, simply take a common and I am just left with the same thing. Okay. Okay. So what is this quantity, by the way? It is f of x. So I have a into f of x. Okay. But this is a into some f. But what is RHS? RHS is just simple y. Sorry, simple f, which implies, okay, So which implies if I assume A into Y is a solution of inhomogeneous part, what I will get? LHS must be equal to RHS, which implies A is equal to 1. Okay. So if A is equal to 1, I'll get a homogeneous solution. If A is not equal to 1 means if A is not equal to 1 implies A into Y naught cannot be a solution for non-homogeneous DE. Okay. So you should know some other way of finding a solution in this case. Okay. What is in this case is there is something called uh, method by some general solutions. Okay. So one example method of finding solution from known solutions. Okay, you can't find the straight away the new solution. If there is already two solutions are existing, in that case you can easily find new solution. Okay, so you are relying on somebody to give you a existing solutions. From there you can find. Okay, because it is not that easy. Okay, one example, non-homogeneous case I am writing y double dash minus y dash minus 2y is equal to 4x square, which is non-homogeneous second order, okay, linear differential equation. Okay, now who can give you a general solutions? You can find out yourself for the homogeneous part. Start with the homogeneous part. Okay, straight away homogeneous part is y double dash minus y dot dash minus 2y is equal to 0. So if you introduce this solution would be exponential sum rx, which implies r values comes out to be some 2 and minus 1. Therefore, y1 of x is exponential 2x, y2 of x is exponential minus x. So these are the two general solutions, are the two solutions for the homogeneous part. From the homogeneous part, I can find the general solution as y is equal to some a into exponential 2x plus b into exponential minus x. Okay. Now, explicit solution I want to find. Okay. Now, finding exact solution. Okay. Which could be a slightly different from this. You know why? Because it is going to be depending on the x component. Okay. So, what I will do? Let's assume y of some homogeneous part is equal to alpha x square plus beta x plus some gamma is the solution for non-homogeneous differential equation. Okay. In this case, you know what happens? If you introduce this back into the above differential equation, you would get, okay, you would be getting the quadratic equation for or the like equations for alpha and beta by substituting above yp of x, we could get, okay, equations for beta and gamma. Okay, by solving those equations, you can find the y of p. Okay, knowing alpha, beta, and gamma, we can write down exact solution. What is the exact solution? Exact solution would be, okay, exact solution would be simply y of px, okay, in terms of alpha, beta, and gamma, okay. You would get, I think, for this case, let me write down from the, okay, for this equation, okay, from the notes I'll write down, alpha comes out to be -2, beta comes out to be 2, gamma comes out to be -3. So y of px is minus 2x square plus 2x minus 3. Okay. So therefore, overall general solution, okay, solution would be y of x is equal to yp of x, okay, plus a into exponential minus plus 2x plus b into exponential minus x. Okay, so this is the overall general solution. Okay, there is a homogeneous part and this is non-homogeneous part. Together it have a entire solution. So this is how, even for non-homogeneous case, even if you have variable coefficients, you can find the solution. At this case, I have constant coefficients. Okay, so we will see for the variable coefficients after the break. Okay, right? Yeah, let me see if there is any questions. Yes, exactly. Oscillator is being forced. The differential equations, whatever we are coming across, more or less, they are the real like oscillator, forced oscillator, this kind of differential equations. Arunima ji, yeah, thank you for mentioning. I will upload. She's asking for yesterday's PPT. I will do that. Yeah, welcome back everyone. I think we can start. So Gauriji was asking again a question for y dash is equal to x square, y dash is equal to x square plus y square. Okay, so y dash for me here is dy by dx is equal to x square plus y square. Okay, so what I see here is if I introduce polar coordinate system, this can be reduced to much simpler case. Okay, in the polar coordinate system, x is equal to r cos theta. Now, I can't have r is constant, so r also has to be a varying function. Okay, so in polar coordinate system, if you just see, if this is Cartesian, radial direction r is varying. Okay, in theta direction, theta is varying. So these are the coordinate systems. Both r is varying, theta is also varying. Okay, right? If I introduce that way, small change in dx, sorry, change in x would be small change in r cos theta. Okay, which would be dr cos theta plus r small change in cos theta. Okay, right? So this is a cos theta dr plus, okay, differentiation of cos theta is minus sin theta minus sin theta d theta into r. So dx is like that. Okay, so dx is cos theta dr minus r sin theta d theta. Okay, similarly you can find what is dy. Okay, so right hand side would become x square plus y square is simply r square. Okay, so dy by dx would be derivative with respect to theta and sorry, derivative with respect derivatives of r and derivatives of theta would be coming here. On the right hand side, I would get r square. From here, you should be able to separate differential equations into derivatives of r, derivatives of theta. If you can do that, then you would get two differential equations which are possible to integrate. Let's try. Dy would be derivative of r sin theta, which is dr sin theta plus r into small change in sin theta, which is dr sin theta plus, okay, just a minute, let me take a call. Mute r cos theta d theta. Okay, so I know what is dx dy. You substitute dx dy by dx. Okay, so you will get two quantities which is equal to r square. From there you try to separate in terms of derivative with respect to r, derivative with respect to theta. Okay, right? Okay, so let's come back for differential equations of variable coefficients. Okay, so differential equations of variable coefficients. Okay, Okay, let me write down y double dash, okay, plus px y dash plus qx into y is equal to r of x. So this is the differential equations I have. I can see it is an inhomogeneous differential equation. Okay, so let's consider only homogeneous for time being. Okay, so what is the homogeneous part? Homogeneous part is y double dash plus p of x y dash plus q of x y is equal to 0. Now, for homogeneous part, we just saw earlier, the solutions would be y1x and some y2x. It is easy to find. Okay, and general solution would be some a into y1x plus b into y2x. Okay, now this is a homogeneous general solution. Okay, but what I want to find inhomogeneous part general solution or any solution per se for the inhomogeneous part. Okay, so that was not that easy. So what I will do, I'll just assume that, let's assume that, okay, a and b may become some function of x, okay, and I'll have some inhomogeneous solution. Let me take as a y naught as v1x y1x plus v2x y2x as a solution is a solution of entire non-homogeneous, okay, equation. Entire inhomogeneous equation I am assuming. Okay, now where v1x v2x are some choice of functions, or some choice of functions. Okay, how do I find some choice of functions? Okay, probably by some technique. Let's say from that way I found. If that is the case, what happens? Let's see. Okay, now y not y dash x would be, okay, so derivative of x of that whatever I have chosen, v1 of x, y1 of x, v2 of x, y2 of x. Okay, right? So, 1 minute, let me connect some power cut here. Yeah. Now derivative means there are two terms here, there are two terms on the second case. So I'll get another extra two terms each. So which is y naught x is, okay, carefully if you just see now, I'll write down v1 of x multiplied by y1 of x. Okay, so first time I'll differentiate with respect to x. Second time I differentiate with respect to, so differentiate y1. So this is one term. So other term is v2 dash plus v2 y2 dash x. Okay, let's just do the rearrangement. Okay, I want to have v1x y1x plus v2 dash x y2 dash x. So this and this term together and the other two terms together, v1x y1x v2x y2x with a dash. Now if you carefully look at this, I can assume, okay, without loss of any generality, okay, let's mandate The first term is 0. You will see why I have mandated that. Okay. If I mandate the first term, what happens? I can say v1 dash x y1x v2 dash x y2x is equal to 0. Okay, right? This is equal to 0. And what is the other equation? v1 x y1 dash x v2 dash x. Sorry. Okay, just a minute. v2x v2x plus y2 dash x is equal to, what is this equal to? Okay, what is this equal to? This is equal to y double dash. Okay, right? Sorry, this is y dash, not y double dash. This is y dash. Now I know what is y dash. I can find y2, y double dash. Again, you just do the same technique. This time you will not mandate anything. Okay, so from here, okay, the first element will be v1 dash x y1x y1 dash v1x y1 double dash x. Okay, one term we got. The second term v2 dash x, okay, y2 dash x v2x y2 double dash x. Very good. I got y double dash. Now I know what is y dash, y double dash. Let's put this back into the actual equation. Okay, when you substitute back into the actual equation, what is the actual equation for you? Actual equation is y double dash plus px y dash plus qx y is equal to rx. This is the actual equation. Okay, substitution into actual equation. Okay, when you substitute, what happens? You just see, it's a very interesting. Now what you are going to see is, you are going to I'll not exactly substitute, I'll take it from my notes and write down what is this expression would look like. The expression would look like v1 into y1 double dash plus p of x y1 dash plus q of x y1 plus v2 into, again, y2 double dash plus p of x y2 plus q of x y2 plus v1 y1 dash plus v2 y2 dash is equal to r of x. This is what I get. By the way, y1 and y2 are solutions of homogeneous parts. What is the homogeneous part? Homogeneous part is y1 y double dash p into y dash plus q into y is equal to 0. So y1 is a solution of this differential equation. Y2 is also solution of this differential homogeneous part, which means this, okay, this entire thing, I'm sorry, I missed putting a bracket. Okay, sorry, there is no need. Undo. Okay, so this entire thing, if you see, it is 0. This entire thing, if you see, is 0. So what you left with? You left with one simple equation, which is v1 y1 prime v2 y2 prime or y2 dash r is equal to r of x. Okay, earlier I have mandated one equation. What is the mandation? v1 dash y1 v2 dash y2 is equal to 0. Beautiful, right? I got two equations with the two unknowns. Okay, so I need to find what is the V1, V2. I just want to find only V1, V2. Okay. First of all, I'll find in terms of V1 dash and V2 dash. Then I can go on to solve for V1 dash and V2 dash, and then solve for V1 and V2. By the moment you get V1 and V2, you can get actual solution, and then you can write the actual solution. Okay, fine. So yeah, so yeah, Manjoti ji was asking V1 Y1 dash plus V2 Y2 dash is equal to Rx is not getting. Okay, so let me go back. Maybe let me use my hand notes to explain what I mean by that. Okay, it's easy in that way. Okay, just a minute. I'll just pick up the page where we are at. Okay, not this lecture. Okay, let me go to the other lecture. Yeah, this is the one. No, not this one. Yeah. Yes, this is the lecture. Okay. So we are doing for variable coefficients. Okay. I assumed, see, homogeneous part. Okay. Homogeneous part solution. Okay. For this is homogeneous equation. The homogeneous solutions are simple exponential functions. From there, I can write a general solution. Okay. Right. But I want to have non-homogeneous case. Na? I assume that A and B are the functions of x, because non-homogeneous R of x is coming into the picture. Because of that, I introduce A to V of x or V1 of x, B to V2 of x, as we have non-homogeneity. Okay. Now, the general solution for non-homogeneous equation is that. Now let me find out what is a y double dash x. So y dash x. Y dash x, I will get, see, you differentiate this, you'll get two terms. If differentiate second, you'll get two terms. Just rearrange. In the first case, I'll have v1 dash and v2 dash. The second case, I'll have y1 dash and y2 dash. Okay. Now, what I'll do, this entire thing I mandate to be 0. Okay. Right? Why I mandated is, I'll assume that the derivative of v1, v2 together, if I take in that way, it's becomes 0. Okay. So without loss of generality, it is called without loss of generality. Okay. And you would see the implication later. Right now, let's assume that. In that case, what happens? I will get y1, y0 dash with only this term. Okay. Now, for having y dash like this, what is the y double dash would be? Again, you differentiate the first two terms and then second two terms. You will get 4 more terms. Okay, let's substitute y0, y0 dash, y0 double dash into actual equation. What is the actual equation? This is the actual equation. Sorry, this is the actual equation. If you substitute into actual equation, if you see it, okay, if you substitute into actual equation, just do some rearrangement, what you see is this is the final form it will appear. Now in the final form, if you see carefully, this is a homogeneous part with y1 as a solution. This is a homogeneous part as a y2 solution. So both are actually 0, because homogeneous solutions means they are equal to 0. That is what I have written here. The first two terms are becoming 0. What is left with? V1 prime, sorry, v1 dash y1 dash plus v2 dash y2 dash is equal to Rx. Okay. Earlier I mandated this or assumed this. So I have two equations for v1 and v2. There is a v1 dash and v2 dash is there. Now I want to find what is a v1 prime and v2 prime. Okay. So first I will find for the v1 prime and v2 prime. Later I will find what is explicitly v1, v2. Now just for convenience or the comfortability, understanding, let's take one example. Okay. And by the example, you will understand what I mean by that. Okay. So let's take an example. Okay. Which example I'm going to take is y double dash plus y is equal to cosec x or inverse, sorry, 1 by sin x. Okay. What is a homogeneous part? It is non-homogeneous linear differential equation. Now homogeneous part, if you just take homogeneous part is y double dash plus y is equal to 0. That's all. There is no first order derivative. So what you can find? You can find the solutions of this differential equation, either exponential function or sine or cosine function. You can cross check y1 of x is equal to sine x. Okay, y2 of x is equal to cos x. If you just check, these are going to satisfy this differential equation. You know why? Y1 double dash is derivative of x sin x, which is derivative of x cos x, which is minus sin x. Y1 dash, okay, there is no y1 dash. So in our equation, there is no need to find. So you can just substitute this back into the above equation. What you will get? Minus sin x into above equation. Okay, right? What you get is minus sin x plus what is y? Y is sin x. Okay, LHS is 0. So I am getting RHS. So this is a solution. Similarly, cos x is also solution. Beautiful. I just got two solutions. Now what I'll do? I'll write a general solution for homogeneous part. General solution for homogeneous part. How to do that? Very simple. You take the average of both of, for superposition of both of them, which I call, okay, some y of x is equal to some a y1x plus b y2x, which is a sin x plus b cos x. But I want a solution for non-homogeneous. For a non-homogeneous, now for non-homogeneous part. Okay, for a non-homogeneous part, I will say the solution would be some y0 x with a replaced by v1x sin x, b replaced by v2x cos x. Okay, fine. So if you want, you put up brackets. Okay, what it says, v1 and v2 are the functions of x we need to find. Earlier, we have two solutions, two equations for v1 and v2. What is that equations? Let me write down. One is v1 y1, v2 dash y2 is equal to 0. v1 y2 y1 prime. 1 minute. y1 prime, v2 y2 prime is equal to r of x. What is r of x in our equation? R of x in our equation is cosec x. Okay, r of x is a cosec x. What is 1 by sin x? Okay, this is what I have. I want to find what is the v1 prime and v2 prime. Let's take it from the first equation. From the first equation, it is straightforward. V1 prime is equal to minus V2 prime Y2 by Y1. Okay. Now, by the way, I just found what is a V1 prime. Okay. So I wanted to substitute back into these equations where minus V2 prime, Y2 is cos x and Y1 is sin x. Basically, it is a cot x. Okay. So V1 prime I know. Now I want to know what is the V2 prime. So from here you take, okay, or you do one thing. Let's do one thing. Let's substitute back into the old equation and then exactly get what is a, okay. Yeah. So I just got, okay, V2 prime, right? So now what you will have minus V2 prime cos x by sin x. Okay, right? Okay, so I'm just writing for here v into y1 plus v2 prime into y2 is equal to 0. What is a y1 y2? So here y1 is 1 minute, v1 prime y1, yeah. So I made a mistake, something. Yeah. So what is the second equation? Let's take it from the notes. Second equation. Okay. Yeah. The second equation is this. I'm sorry. I missed V1 primes also. Okay. So let's get back. That's what a mistake. So V1 prime, V2 prime. Now it makes sense. Okay. In place of V1 prime, I substituted V2 prime cos x, and what I'll have y1 prime. Y1 prime means derivative of sin x, that is a cos x. Okay, in this place I'll have a cos x, and v2 prime y2 dash. So y2 dash is derivative of cos, which is a minus sign. So let me remove that and just substitute minus sin x. Right? So now, which is equal to, I'm sorry, which is equal to cosec x. Okay. So this is into above equation. Now, if you carefully write down this, and this is 1 over sine and this is sine. So you send this to or multiply the entire equation by sine x. What you will get is minus v2 prime cos square x minus v2 prime sin square x is equal to 1. Okay. So you take a minus v2 primes common, you will get sin x plus cos square x is equal to 1. Sin square x plus cos square is equal to 1. So which implies v2 prime is equal to minus 1. So v2 prime means what? dv2 by dx is equal to minus 1. From here you can find out dv2 is equal to minus dx. So v2 is simply x. Okay, right? Similarly, the moment you know v2 prime, 5 o'clock. Okay, so the moment you know v2 prime, you can v1, v2 and v2 prime, you can find v1 prime, which is minus v2 prime y2 by y1, right? So this is equal to minus 1 of minus 1 cos x plus sin x is equal to cot x. Okay. So having known dv1 by dx is cot x, you can easily find what is v1. How? You can just do dv1 by dx is cos x by sin x. Okay, dv1 is cos x by sin x into dx. Now let sin x, sorry, let sin x is equal to t implies derivative of sin x is a cos x, dx is equal to dt. So which implies dv1 is, okay, dt by t. Now integrate. When you integrate, on the left hand side, you get a v1, on the right hand side, you get a log of, natural log of t plus some constant. Let's say c prime. Okay, right? Fine. So what is a t, by the way? T is log sine of t plus some c prime. Okay. So v1 I got, v2 I got. From there, you can easily find what is the actual solution. What is the actual solution is y naught x is v1 is log of sin x into sin x plus what is a v2 minus 1 into x na minus 1 into x, and y2 is cos x. Okay, so you got the solution for the even the case of even for the case of inhomogeneous differential second order differential equation with the variable coefficients. Okay, so by knowing one solution, getting further solutions is also very easy. So there is something called exponent method. Okay, so it is there in the notes, you can just check. By using exponent method, we can find other solutions if you want more solutions, by the way. Okay, so what I mean is this one. 1 minute, let me show you. Finding new known solutions from the known solutions. So, okay, so the exponent method is this method. Okay, so we'll find some v of x, multiply it to the old solution, gives you a new solution. What is a v of x? V of x is some exponent which is constructed out of old solution. Okay, fine. So these are the differential equations. Any other? Okay, some examples I have in my notes. You can cross check. Okay. Okay, so some example. There is another case which is slightly complicated. It's called exact equations, differential equations by exact equation. If I'm having a partial differential equation where the functions are depending on x and y and derivatives are x and y, where let's say here x and y are the independent variables and I have a function m and n, they are the depending on x and y. In that case, how do I solve? Okay, so this itself takes about half an hour or so. We are not going to get into this. For as an additional exercise, I have given how to solve these things along with the example for you people. Please cross check. Okay, right? So see, I can tell you how many slides it will go. It will go for another 4 to 5 slides. That's why I'm not getting into it. Now coming back to the numerical integration. Okay, right? So now let's see. We have promised for you what I have promised so far. Okay, initially. Okay, let me go there. Yeah, linear differential equations of second order with constant coefficients, linear second order differential equations with variable coefficients. We covered both of them. What else I have to cover? I have to cover numerical integration. Boundary value problems, of course, we have touched them. Okay, so numerical integration, we'll just check straight away from the notes. Since we have 15 minutes time, I'll not waste any more time. So I'll straight away use my notes and I will discuss. Okay, by the way, all our differential equations, whatever we have seen, are represented as a derivative equal to some functional. Okay, so functional form f is actually called derivative function. It is called derivative function, or even sometimes it is called a force function. Okay, in numerical integration, it is called. So numerical integration is a technique which is done by iterative method. You integrate a given differential equation using iterative method on a computer using some program. Okay, so for doing it, the main logic behind is you take the same differential equation, the simplest one. Okay, and on the left hand side I have a derivative. What is the literal definition of a derivative is the function y value. Yeah, definitely I will share these notes, Santosh ji, don't worry. Okay, so derivative of y with respect to time means y value at t plus delta t minus y value at a t divided by small change in delta t, where delta t tends to 0. This is a definition of derivative. Okay, now let's take exclude the limit and say dy by dt is approximately this fraction. Now let's do some rearrangement. Okay, the rearrangement is this is equal to f of y comma t. Okay, the function value at later times is equal to function value at older times plus some step size delta t multiplied by the derivative function. By the way, dy by dt is equal to derivative function means what? On the left hand side is a derivative, is a slope. So this is a slope function. F of y comma t is a simple slope function. This is a slope. Okay, right? So what I have to do to find the new value, I have to take old value. For that, I have to add a small correction term. How do I generate the correction term? I'll for the given derivative equation, I'll multiply it by small steps. You will get the correction. So this is Euler's method. So geometrical interpretation of this method is, okay, let's say if I know, let's say if I know in advance what is my y of t with respect to time t, okay, the solution of this differential equation is, let's say, some curve like this. Okay, right? Fine, this is a curve. Now the Euler method is, what it does is it uses the old value and draws a slope at the old value, and for that slope it multiplies a step size. Okay, the moment you multiply a step size to the slope, what you will get? You will get a small correction term. This is a delta t into f of y comma t. Okay, let me write down neatly. Okay, right? So this is a, yeah, I have written already, this is slope function. Now for the slope function, you are adding a multiplied by delta t. What you are going to get? You are going to get this correction term. This is delta t into f. That much value are going to add to the old value y. Okay, so y at t, and for that you are going to add this much correction. What you are going to get? You are getting a new point. This is a new point. Okay, but what is your actual equation? Actual curve. Actual curve is, if you see, notice this is the actual curve. Okay, but the thing is, Euler method is giving a solution at a error of this much error. Okay, error. But don't worry, at least we are going very close to the curve. Okay, so Euler method numerically it calculates the new value slightly away from the curve. Let's say I am satisfied, and if I continue to do the same thing for the later point, what happens? I am just keep going and deviating and deviating. That is what happens. Okay, here, right? So this is the actual curve. If you see, this is the actual curve. Your Euler method keeps deviating continuously. So the curve we are getting is initially maybe close, but later on late like this. So from the actual curve, you are deviating a lot. This is the happening because of the error in every calculation. Okay. So why? Because if you expand, okay, let me show you where the error is coming again. Okay, right? Yeah, here it is. Okay, so if you do the Taylor's expansion of y of y for a small change, for a small change in y, you would have expansion terms, higher order terms, and so on. But all those terms we are ignoring. We are even ignoring from the h square terms itself. Small step size here, delta t is a h. So I'm expanding f y plus h. Okay. So because of that, what happens? The error creeps in. I'm going away and away from that. So people have come up with a new correction term. It is called Cramer's correction. What is a Cramer's correction? Is, say, using the old value, using a derivative function, multiplying the derivative function with delta t, you get a new value now. So which is away from the actual equation, actual curve. So what you do is, please take that new point, again you draw a slope at that new point. Instead of using a old slope, you use a new slope. So that is this one. So the first step is find the new point and treat that is some kind of intermediate point. Let's say we go to a destination via some point. Now, like that, you take the new point as some point where I am not going to satisfy. I'll take a derivative at that function and you multiply the derivative of that new value with the delta t and do the correction, add it to the x1. What you do in this case, you will get a most corrected. Instead of having a lot of error, you will get a less error. So this is the idea, is just exploited and incremented but updated by Runge-Kutta. What they did, instead of taking multiple slopes, they took slopes twice. One is at the initial point, another is a later point. They took the average of both the slopes and used that for the correction. See, average at the slope at the old, slope at the new, and their average, and multiply to delta t. This is the RK2 method. Okay, so there is a theoretical explanation for this. You can follow it. Okay, and the error happens here of the order of 10 to delta t to the power of 3. Okay. Okay, so there is a RK4 method. Instead of taking 2 slopes, you take a multiple 4 slopes, 1, 2, 3, 4 on the curve. Okay, for 4 different points, you find the slopes and you take the average of all the slopes. Okay, all right. So here you will get 1 by 6 because the second slope and third slope contribute twice. That's why I'll have 1 by 6 instead of having 1 by 4. And with this, the error could be reduced to delta t to the power of 4 odds onwards. So in Euler's case, delta t square itself the error is happening. In Runge-Kutta, r delta 3, delta t. So okay, let me write down. Euler case, error is delta 2 square onwards. Okay, so RK2 case, delta t to the power of 3. RK4 case, delta t to the power of 4 onwards, the errors are occurring. Okay, that is the beauty of error correction in the case of Newton-Raphson method. Sorry, in the case of numerical integration. So this is just for your reference. So some boundary value problem specifically with some examples I have given. You just go through it. Okay, right? So that is about it. For programming, I think most of you are already comfortable in programming. So what I will do, I'll share you another notes. Okay, so which discusses about programming. So solving using Euler. See Euler case. You see the actual curve is this. This is the actual curve. Your Euler method is deviating like this. Okay, the moment you add a Cramer's correction, you come very close. Okay, so one of the example is freely falling body. How do I solve using Euler method? Okay, right. So the Python programming is discussed. Okay, so this is a specific Python programming. There is a separate function I used for Euler method, and I would be using some derivative function. In that case, I'll have derives function. And here, if you see, I'm plotting the velocity of the particle falling body, and also its a position with respect to time. If you just integrate, you would see position is decreasing and velocity is also decreasing. And here I have not imposed the condition where after hitting the center, like a surface of the object, after hitting the surface, it is going within the surface. That is, you can avoid by putting a condition where the moment particle hits the surface, it stops. So that condition you can impose. That is what I did here. You see the position, the red color is position. Okay, I have it, I think later. Yeah, this is the one. Okay, so position hitting the zero, it stops, but velocity is negative, means it is accelerating towards the surface. Okay, right. Okay, so now the real world scenario, spring mass system, how do I solve? Okay, so you introduce new variable, which is a velocity variable, and convert second order differential equation into first order. Okay, so it becomes two first order differential equations, and the program is discussed. I'm not getting into the detail. And if you integrate, you would get a nice oscillatory solution. But there is a problem. So see, any given pendulum should not oscillate forever. Means it is increasing the amplitude. It's not the case. This is happening because my Euler method is having errors creeping in continuously. Because of that, something absurd situation is coming. The moment I add a Cramer's correction, I see. Okay, so even if you integrate for a longer time, you see expanding. So with a Cramer's correction, if you integrate, you see the amplitude is decreasing. Means the oscillations are diced down. This is the actual solution. Okay, you can use the RK2 method even for that case. Okay, you can get much more accurate solutions. Okay, so there is a theoretical explanation why RK2 method and RK4 method works. That is discussed here in my notes. I will request all of you to please cross check and how RK2 method is correct up to delta t square, how RK4 method is correct up to delta t to the power of 4. So that is also described in detail in my notes. And I don't think any books discusses how geometrically RK4 method works. So I have it for you here. So you can cross check that also in my notes. Okay. So there is something called Monte Carlo integration. Let's say higher dimensional quantum systems are there. There is a lot of integrals are there, multiple, double, triple integral are there. In that case, we can't do the integration. Okay, so there is something called Monte Carlo integration is going to be very, very helpful there. What is this Monte Carlo integration is? You can understand in the case of double integral. Let's say I have a curve, okay, which is described by dy by dx. Okay, so what is the solution? Solution of the curve would be a area inside this curve. Okay, what I will do, I will enclose that area into a known shape, and I will drop points within this entire surface. I'll count the number of points falling inside the shape, number of points falling overall. So indirectly what I say is the ratio of number of points falling in, random numbers falling in, divided by total number of points is actually the ratio of the area of this odd shape divided by entire area of this rectangle in this case. So in that way, we can do Monte Carlo integration without bothering about integral techniques. Okay. So one of the example I have discussed for you. Okay. For example, I want to find the area under this 1/4 of a circle. So how do you do it? That is discussed here. You can just cross check. Okay. So the program is also discussed. I will share the some programs in my notes. The program is discussed step by step. You can cross check. Okay. So let me see. There is any question. Where we use boundary values in real time. In real time, probably the qubits are enclosed within a surface or within a three-dimensional surface. In the case of, let's say, uh, for example, trapped ions or let's say even quantum dots. In those cases, we are confining within certain region. There probably might need to know what is the behavior of these quantum systems within those boundaries. So mathematically, if you want to model it, so there you would be needing it. Okay, right? So yeah, the applications are, if you want to develop a mathematical model which describes the quantum systems behaving dynamically in time, in space, there all these things are going to be very, very handy. Okay, right? So not only this, somebody dealing with any dynamical system, whatever methods which we discussed are going to be very useful. Fine. So I'll stop at this point. Yeah. So probably, yeah, tomorrow let me see what is tomorrow schedule for you. Yeah, it's going to be quantum simulations using Qiskit and Penny Lane and a quantum simulator and Q inverse. So using that, you are literally going to understand how quantum systems can be simulated and programmed. That is going to be discussed for tomorrow onwards by Dr. Jay Kumar. So you will have fun and learning those things. Whatever I discussed yesterday and today is a basic mathematical physics, which is going to be required for you to have a hardware understanding, hardware designing when it comes to quantum circuits and quantum qubits. Okay, fine. So I'll stop at this point and I'll hand it over to the I'll hand it over to Academy. Yeah, I have already shared the entire notes. Okay, so I'll quickly share my this also, hand notes also. 29th October. So in the canvas I have shared. Okay, so you pick any differential equations references, you would easily understand whatever things I have discussed in length. Okay, so upload file.
Thank you so much, Ashwath sir.
Thank you, ma'am.
Sir, actually, sir is busy in a meeting, so I think we can conclude the session now.
Yes, ma'am. Yes, yes.
So thank you so
Yeah,
much, sir.
yes, ma'am. Hello, thank you, ma'am.
Thank you,
So,
participants. Yes, sir.
yeah, I have uploaded even today's part to the drive. Yeah.
Okay, sir.
Okay, then.
Okay,
Thank you,
sir.
ma'am. See you.
Thank you, sir. Thank you. And participants will be having the session tomorrow from 3 to 5. Okay. Thank you so much, participants.
Thank you everyone for nice kind words. I'll get back to you people at the later